I want to start today with a contradiction. It's one of those things in physics we sort of take for granted, but if you really stop and think about it, it doesn't quite add up.
Oh, yeah. Which fundamental contradiction is it this week?
It's the battle between stuff and structure. On one hand, you've got the building blocks, the particles, electrons, atoms, all the physical things.
The bricks.
The bricks, exactly. And on the other hand, you have the structure, the geometry, the way those bricks are arranged to make a wall.
Right. And the assumption is always that you need the bricks to have the wall. Simple cause and effect.
Yes. If you smash the bricks into dust, the wall is gone. The structure vanishes with the stuff. It's intuitive.
It is the intuitive view of reality, yes.
What if it's wrong? What if you could push a material to such an extreme point that the bricks, the particles themselves, effectively dissolve into this kind of quantum soup, and yet the wall is still there? A rigid mathematical structure just remains.
Okay, that sounds like you're describing a ghost. Like the architectural blueprint of a house hanging in the air after the house itself is gone.
It does, but apparently it's not a ghost. It's something called a Weyl-Kondo semimetal.
Ah, I see where this is going. You've been reading the latest Nature physics, haven't you?
I have, and this paper, Emergent Topological Semimetal from Quantum Criticality, it's bending my brain a little. It's from Kirschbaum, Chen, Passion, and a whole team of colleagues, and what they're claiming here feels massive.
It is massive. It's a fundamental challenge to how we think about order and phase transitions. They've essentially found a way to decouple the topology, the mathematical shape of a material's electronic properties, from the very particles that are supposed to create it.
So that's our mission for this deep dive. How is that possible? How do you get a traffic pattern without any cars? And what does it mean for material science if we can start building things out of, quantum soup?
To even begin to get our heads around it, we have to start with the material. Because you can't find this kind of weirdness in just a lump of iron. You need a very specific, very strange setup.
Okay, let's introduce our protagonist then. The material is cerium ruthenium tin, or 0,4SN6
And this belongs to a class of materials that I just find fascinating. Heavy-Fermion compounds.
Heavy-Fermion always sounds like a bit of an insult to me. But in physics, it's a literal description of what's happening, isn't it?
It really is. Normally, an electron has a fixed mass, and in a normal metal, it zips around like a race car. Very fast, very light.
But not here.
Not here, no. In this cerium compound, the crystal is filled with these little magnetic moments from the cerium atoms. Think of them as tiny sticky traps scattered all over the racetrack.
Okay, so obstacles.
Exactly. And as the conduction electrons try to move past, they get caught up in these magnetic interactions. It's something called the Kondo effect. It's like trying to run through a swamp. The electrons get seriously bogged down.
They slow down.
Drastically. And because they're moving so slowly, they act as if they are incredibly heavy, sometimes hundreds, even 1,000 times heavier than a free electron.
So we've got these sluggish, overweight electrons just kind of trudging through this crystal.
And because they're so slow, they interact with each other really strongly. They stop behaving like individuals and start acting like a collective fluid. We call the excitations in that fluid quasiparticles.
I love that word, quasiparticle. It's like admitting, look, it's not really a particle, but it acts enough like one that we can do the math.
It's a convenient fiction. That's what it is. But there are two other crucial details about this material. It's a semimetal, and it's non-centrosymmetric.
Okay, break those down. Semimetal just means it conducts electricity, but not very well.
That's the gist of it, yeah. But non-centrosymmetric is the real kicker for the weird geometry. It means the crystal lacks inversion symmetry.
So if you flipped it inside out, it wouldn't look the same. It has a handedness to it.
Like your left and right hand,
Yeah.
exactly. And that broken symmetry is a crucial ingredient. It allows for all sorts of exotic electronic behavior that's forbidden in more symmetric crystals. Okay, so we have a lopsided crystal filled with these heavy, slow quasiparticles. But the researchers didn't just look at it. They basically tortured it.
They pushed it right to its quantum critical point.
That's a term that gets thrown around a lot. What does it actually mean in this context?
Well, think of a normal phase transition, like ice melting. That happens at a specific temperature, and it's driven by heat thermal fluctuations jiggling the atoms apart.
Right.
A quantum critical point, or QCP, is a phase transition that happens at absolute zero, 0 Kelvin.
Where there's no heat.
Exactly.
Yeah.
So with no thermal jiggling, any transition has to be driven by something else.
Quantum fluctuations.
The raw uncertainty of quantum mechanics itself. The researchers use a tuning knob, like pressure, to push the material right to this tipping point where its fundamental state changes.
So what happens to our heavy quasi-particle friends at that tipping point? Annihilation. Total destruction.
That sounds dramatic.
It is. It's called Kondo destruction. That sticky magnetic screening that created the heavy quasiparticles just collapses. The whole system breaks down.
So our quasiparticles, the fictions we were using to describe the electrons, they just vanish.
They dissolve into a scale-invariant soup.
Yeah.
A fluctuating, entangled mess where you can't point to a distinct particle anymore.
And this brings us right back to the paradox.
It certainly does.
Because the paper claims that in this soup, in the wreckage of the particles, they find a Weyl semimetal.
Yep.
But a Weyl semimetal is a topological state. It's defined by the shape of its electronic bands. And those bands are supposed to be made of, well, particles.
They're made of Bloch states, which are the wave functions of stable quasiparticles. Standard theory requires them.
So if I have this right, they're saying the bricks have turned to dust, but the wall is still standing. How can you have the topology of the bands if the things that make up the bands are gone?
That is the million-dollar question. And for years, the assumption was you can't. You hit a quantum critical point, and any topology should just wash away in the chaos.
But they found the smoking gun. How do you even detect an invisible structure inside a quantum soup?
You look for something called the spontaneous Hall effect.
Okay, the Hall effect. That's when you run a current through something, bring a magnet nearby, and the electrons curve to one side, creating a voltage.
Exactly. The magnetic field pushes the charges sideways. That's the Lorentz force.
But they call it spontaneous, so no magnet.
No magnet. That's the whole mind-bending part. They cooled this 04SN66 down into this quantum critical regime, and they measured a sideways voltage appearing all by itself.
So something is bending the path of the electrons, or whatever is in the soup?
It's as if there's a huge internal magnetic field, but there isn't one.
What's causing it then?
The topology itself. There's a property in momentum space called Berry curvature.
Is that like a warp in the fabric of the electronic states?
That's a great way to think about it. The landscape the electrons move through isn't flat.
Mm-hmm.
And in a Weyl semimetal, there are these specific points, these Weyl nodes.
The nodes.
And they act like sources and sinks for this curvature. They behave like magnetic monopoles, twisting the flow of current.
So seeing this spontaneous Hall voltage is direct proof that those nodes are there. Proof that the landscape is twisted, even if the travelers are completely lost in the fog.
Precisely. It's the unique fingerprint of this topological phase. But here's the part of the data that really blew me away.
The dome.
The dome. They didn't just measure at the critical point. They used pressure to tune the material away from it, back towards a more normal, stable state where the quasiparticles were formed.
So they rebuilt the bricks, restored order.
And as soon as they did, the signal went away.
Wait, the topology vanished.
It vanished. The topological phase exists in a dome right on top of the quantum critical point. As soon as you move away from the chaos, the structure disappears.
That's completely backward. You're telling me that making the system orderly and stable destroys the structure, but letting it dissolve into a chaotic quantum mess creates it.
It implies the quantum critical fluctuations aren't the enemy of the topology. They're the very thing that stabilizes it. The chaos is the lifeblood of this phase.
Okay, we have the evidence. The ghost is real and it feeds on chaos. Now, for the how. The paper's theory section, led by Kimiosi's group, had to throw out the standard toolkit for this, right?
They absolutely had to. You can't use Bloch states and simple wave functions when you don't have them.
So they use something called Green's functions instead.
Right. It gets a bit technical, but the idea is if you can't track an individual particle's path, you can still track how a disturbance spreads.
A ripple in the pond.
Pretty much.
Yeah.
A Green's function tells you, if I poke this system here, how does that poke propagate and affect the system over there? It lets you look at something called the single particle spectral function.
Which, what exactly?
Think of it as peaks in the energy landscape. Even if the electrons are a mess, the system still has preferred energies. There are still ridges and valleys, even if the hikers are gone.
And this is where the lopsided crystal comes back into play, the non-centrosymmetric part.
Yes,
Yeah.
because even as the electrons dissolve, the crystal lattice itself, the heavy cerium and tin atoms, that framework is still there. It's rigid.
The cage is intact.
And the symmetry of that cage imposes rules. It constrains what those spectral functions can do. It forces those energy peaks to cross each other at specific points in momentum space.
The Weyl nodes.
The Weyl nodes. The underlying symmetry of the crystal lattice protects them.
I think I need an analogy here.
Okay, Imagine a river with whitewater rapids. The water is completely turbulent and chaotic. You can't track a single molecule of water. That's our quantum critical soup.
Wait.
But imagine there are large immovable boulders fixed in the riverbed in a specific lopsided pattern.
The crystal symmetry.
Exactly. Even though the water itself is a chaotic mess, those boulders will force the flow into a predictable pattern. You'll get stable whirlpools and eddies in very specific locations.
Ah, so the shape of the flow, the topology, is dictated by the fixed boulders, not the chaotic water.
You got it. The Weyl nodes are the whirlpools. They're anchored by symmetry. The Green's function math proved that these nodes survive the destruction of the particles because they're protected by something more fundamental.
And there was one more piece of data that really drove this home for me. They measured the velocity of the whatever's moving.
The Weyl velocity, yes. How fast these effective excitations propagate through the nodes.
And it changed with pressure.
It did. As they tuned the system closer and closer to the critical point, the velocity just plummeted.
What does that mean?
In physics terms, it means the energy bands are getting flatter. A flat band means the kinetic energy is very low.
Which means
it means the interaction energy is dominating. The particles, or what's left of them, are spending all their time talking to each other instead of moving around. They're maximally correlated.
So the fact that the velocity bottoms out right at the critical point is proof that these intense interactions, the Heavy-Fermion physics, is what's generating the topology.
That's the connection. It links the heavy physics directly to the Weyl physics. They're two sides of the same coin.
Which basically solves the paradox. You don't need the individual bricks if the mortar, the interactions, is strong enough to hold the shape on its own, guided by the foundation of symmetry.
And that's a profound shift in how we can think about a phase of matter.
Okay, let's get to the so what here. Because this sounds incredible, but is this just exotic physics, or can you, do something with it?
Well, it's not going to give you a quantum toaster tomorrow, but it points towards a whole new class of sensors. To see why, you have to compare it to the other famous phase that shows up near quantum criticality. Superconductivity.
Right, the holy grail, zero resistance.
Superconductivity sees all this quantum critical chaos and basically says, I want out.
It finds a way to create order.
It forces electrons into pairs, forms a condensate, and lowers its entropy to escape the fluctuations. It restores the quasiparticles to save itself.
So superconductivity is a flight from the chaos.
Yes, but this Weyl-Kondo semimetal does the exact opposite. It embraces the chaos. It lives in it.
It surfs the wave instead of running from it.
Perfectly put, it remains a non-Fermi liquid. The topology and the quantum soup are coexisting, and that changes the entire design principle for finding new materials.
How so?
For decades, the rule has been, if you want a robust topological material for, say, a quantum computer, you look for it in a stable, quiet, well-behaved insulator.
You look for order.
And this paper is shouting, go look in the noise.
Go look in the noise. I love that.
Go look in the most turbulent critical regions of these heavy fermion metals. We've been throwing these regions away thinking they were just messy transitions. It turns out they can host incredibly robust topological states.
And what's the payoff for building a device that works in the noise?
Extreme sensitivity. Systems poised at a critical point are, by definition, exquisitely responsive. A tiny push, a small magnetic field, a single photon can cause a giant response.
The paper mentioned another material, CT3x4PD33, that showed a giant response.
It did. The response in the material we're talking about today is smaller, but it's theoretically pure, right at the critical point. The principle is the same. You're combining the mathematical robustness of topology with the incredible sensitivity of quantum criticality.
It's like having an anchor made of math that's floating on the most sensitive water you can imagine.
That's a really good way to put it. It opens up a new playground for creating sensors or switches that are orders of magnitude more responsive than what we have now.
It really feels like peeling back a layer of reality. We start with a chunk of metal, we freeze it, we watch the particles dissolve, and then a perfect geometric structure crystallizes out of the chaos.
It completely flips our intuition that cold equals simple order. Here, the most sophisticated order emerges from the point of maximum quantum fluctuation. It's not